So, you've probably heard a bunch of acronyms thrown around in the tech world: API, DNS, URL, the list goes on. Today we're diving into one you might not have heard of, but it's quietly doing some heavy lifting behind the scenes: MCP, or Model Context Protocol. At its core, an MCP server is essentially a central hub, a single source of truth for configuration data. Imagine you have a whole fleet of different apps and services that all need to know the same set of rules or settings. Instead of telling each one individually, you just update one place, the MCP server, and it handles the rest. It's like the ultimate settings menu for a complex system. Think about it like this. You have a bunch of smart home devices, lights, a thermostat, a smart speaker, maybe some connected blinds. You want them all to go into movie mode. Instead of going to each device's app and dimming the lights, lowering the temperature, and closing the blinds one by one, you just press one button in a central app. That app acts like a simple MCP server. So, why was MCP even created? The big problem it solves is something called configuration drift. This is what happens when you have a large system with many components, and over time their individual settings start to drift apart. One service gets an update, but another doesn't. A developer manually changes a setting on one server to fix a temporary issue, but forgets to change it back or apply it everywhere else. Before you know it, your system is a tangled mess of inconsistencies. This makes it incredibly difficult to manage, debug, and keep secure. It's like trying to get a band to play a song when everyone has a different version of the sheet music. Before protocols like MCP, managing configurations was a very manual and error-prone process. System administrators would often have to log into dozens or even hundreds of servers individually to update a single setting. They used scripts to try and automate this, but these scripts could be brittle, failing if one machine was offline or had a slightly different setup. This approach just doesn't scale, especially in the modern world of cloud computing and microservices, where you might have thousands of components that are constantly being created, destroyed, and updated. The old way was too slow, too risky, and just couldn't keep up with the pace of modern technology. MCP introduces a much cleaner, more declarative model. Instead of telling each component how to update its configuration, you simply declare what the final desired state should be in the MCP server. The server then acts as the central authority, and clients subscribe to it. Alright, let's break down how an MCP server actually works, step by step. It's simpler than you might think. First, you have the MCP server itself. This is the brain of the operation, holding the master copy of all the configuration data. This data is organized into different collections: network policies, security certificates, endpoints, routes, and other collections. Think of it like a library with different sections for different topics. On the other side, you have the MCP clients, applications, services. They are the library patrons who need specific books. The process begins with a client initiating a connection to the MCP server. When it connects, it basically says, "Hey, I'm a new client, and I'm interested in these specific collections of data." For example, a service mesh proxy might subscribe the endpoints collection, the routes collection, so it knows where to send network traffic. This subscription is a key step. It's not a one-time fetch, it's a long-term relationship. The client tells the server to send all future updates. Like subscribing to a YouTube channel, you get notified of new content. Once subscribed, the MCP server sends the complete, current version of the requested collections. That gets the client up to speed immediately. From then on, communication is server-driven. When an admin updates config, adding a new endpoint or changing a routing rule, the server finds subscribed clients that need that data and pushes only the changes, small delta updates instead of a full resend. This avoids resending the entire configuration and is far more efficient. Clients stay in a listening state. When updates arrive, clients apply them often with no downtime or service interruption. The whole process runs over a streaming connection like gRPC, enabling continuous two-way communication. Client subscribes, initial state, passive incremental updates. In short, clients subscribe, get a snapshot, and receive incremental updates pushed from the server. The result is fast, efficient, and scalable configuration delivery. That saves bandwidth, reduces errors, and keeps teams focused on features. Diving a little deeper, the architecture of an MCP server is designed for simplicity and reliability. There are a few key components: the configuration store, the MCP server logic, and the transport layer. The configuration store could be files on disk, a Git repo, or a database. The MCP server watches it for changes. The server logic manages subscriptions, maps clients to collections, and packages updates with context like version numbers. That context, version, who updated it, timestamp, is crucial for auditability and stability. MCP is transport agnostic but commonly runs over gRPC because of streaming and performance. Streaming keeps connections open so the server can push updates instead of clients polling repeatedly. That makes the whole system fast, scalable, and resilient. Where do you see MCP servers in the wild? A big example is Istio. Istio acts as the control plane, the MCP server, pushing config to Envoy sidecar proxies, the MCP clients. Change a routing rule in one place and Istio distributes it to proxies across the mesh. Another use case is control planes for API gateways. Define routes, rate limits, auth policies centrally. Gateway instances subscribe as clients and receive consistent configs everywhere. Centralized control simplifies auditing and strengthens security posture. MCP provides consistency, faster rollouts, automation, and less human error. It lets teams focus on building features instead of fighting configuration fires. Each piece has one job, and together they make a robust configuration distribution system. Thanks for watching. If you found this useful, like and subscribe for more deep dive explainers.